Okay, well, we'll give it a shot. I don't know if this is going to work or not. So, folks, question I have for you. Everything about this unit is trying to sort of culminate with this project. And so, if you guys survive the first and the second drop, so that'd be a 1 meter drop, that'd be a 2 meter drop. If you survive those, you're going to drop it off the balcony. My question for you would be this. How fast do you think this thing would be moving by the time it hits the ground if dropped from the second floor balcony? I would like it in miles per hour. Right? So if I drop this thing, you guys know that this thing speeds up as it falls. If I drop it from the second floor balcony, about how fast do you think it would be hitting the ground once it falls about 6 meters? How fast? Just take a moment. Tell that person.
There's the next one.
How fast? In miles per hour. And I'm hearing some numbers. The actual number is close to about 22 miles per hour. It's about 22. Now, how I know that has to do with the acceleration due to gravity and things like that. You guys, we have talked about this, that the force of collision on that thing is probably going to be somewhat dependent on speed, how fast it's going. Right? So the faster it's going, the bigger that force will be. We need ways of being able to describe the motion of objects. And so that is sort of our main thing for today, is to talk about how we can start to quantify this thing about speeds and velocities. And forces are related to that, so are things like momentum. And so there are quantities in physics that involve moving objects and speeds. So average speed versus velocity, we're going to do some definitions. This has a little bit of math in it. I try to go as light as possible with the math, but we are going to start looking at just one equation today. We have to be able to use it, and that'll come up numerous times throughout the course. So average speed or velocity. Speed is just simply how far an object travels in a given time interval. Velocity is essentially speed, but with a direction. They're not much different, except that velocity includes direction. Now, this morning I'm driving in from my home. I live north of town, so I'm driving down US 31. My speedometer is reading 62 miles per hour. That'd be my speed. On my rear view mirror, there's a little S on that rear view mirror that says, I'm not just going 62 miles per hour. My rear view mirror says I'm going southward. With that south, I could say what my velocity is, because velocity just includes in direction. So speed and velocity, almost the same thing. Velocity just has a direction with it. We can calculate the speed with distance traveled divided by time elapsed. That'd be an average value. So how far do I travel in a certain amount of time? We will often use equations with symbols instead of words. And that's just a concise way of writing a word equation. We just write it as a symbol equation. Now, someone's going to ask, do I have to memorize these equations? And I would say no. You will have access to any equation that we would need for calculating things. You would have access to that. I give that to you in an equation sheet. You can often we'll allow kids to bring in their own equation sheet. They can write things on an index card. So you don't have to memorize them. And Elena, you're from where again?
Spain.
From Spain. When you take physics, and I know you have to in Spain, every kid has to take physics there just like we have here. Do you have to memorize all those equations in Spain? Yes. So we don't have you memorize them here. So we have them, you have access to them, you just have to sort of know when and how to use them, okay? All right, so speed is distance over time. Now, miles per hour and kilometers per hour are the ones that you're probably familiar with. The SI unit, the unit that we would use, is meter per second. So when we do measurements in class, and I have you guys do some things with those red buggy cars, we'll use the meter per second as the unit. Okay? Now, the table to the right has both meters per second and miles per hour and kilometers per hour. You guys are probably most familiar with the center column. Like, you know what those speeds feel like. Well, hopefully you don't know what 112 feels like if you're driving in a car. But there are places up north where the speed limit is approaching 80, so you probably know what some of those things feel like. These are the equivalent values in meters per second. These would be what the equivalents are in kilometers per hour. can you use some reasoning to figure out what goes in that blank there? Can you use some reasoning to figure out what goes in that blank? Thank you, Caleb. We don't throw things in class. Can you figure out what goes into this blank? Thank you so much. Thank you. And how you did that probably was you recognize that this is a twofold increase when I go from 5 to 10, so same thing there, right? It's just, that's what we call proportional reasoning. Just proportionalities. With the same logic, you can determine that this, if I go from 5 to 50, that this would also be a tenfold increase, and that would go to 180. Now, that table's there so you can get a sense of what you already feel comfortable with, miles per hour, but how they're related to things in meters per second. Now, I would like to convince you that the speed limit signs out there should really be velocity limits. I'm going to share a story with you. The only difference between velocity and speed is that velocity includes the direction. I'm driving down South Florida about 5 years ago with my family, and I get off on I-75. I'm going south. I-75 is the main interstate that you would take to go from Michigan to Florida. Get off on I-75 down to Lake Tennessee area, and when I get back on, after getting gas and a cheeseburger or whatnot, I end up getting on the wrong ramp, and I end up going south in the northbound lane. Generally not a good idea, right, to be driving the wrong way on the interstate. I was not violating the speed limit. My speed was fine. But I was violating the velocity limit, meaning velocity includes the direction, and we want to make sure that we're going the right way there. So I would say it should really be a velocity limit. Thankfully, I was able to get off and not have any accidents, but it really is a velocity limit that we're concerned about. Now, the other day, and I can't remember who it was, I had twirling the bumblebee around on the string. Who was it that was doing that with me? Nate. Okay, yep, and it's gone now. An object that is moving around in a circle could be traveling at a constant speed, but because its direction is changing, we would say that it's not a constant velocity. We would say it's a change in velocity. Changing velocity requires unbalanced forces. So if we're turning, we have to have some forces there to be able to do that. Okay, now I've got to show you guys how to use this equation. Speed is distance over time is just one of our equations. We'll probably have over the course of the semester, we'll probably have about 20 equations that we'll have to use at various times. So this is our first one. I want to go through and do just a few problems with you. We'll stop at that point, give you guys an activity to do with using that equation, and then we'll move right into that formative, and that'll be it for the day. Now, the way that I would write this equation is speed is distance over time. I could rearrange that equation to be distance is speed times time. And I could write that equation one final way with time as distance over speed. It's all the same equation, just solved for a different variable. For those of you that math is your strong suit, that is probably easy for you to go through and change that equation around. For a lot of people, math is not their strong suit. So that equation can be written in 3 different ways, solving for different variables. I know we have some runners in here. Raise your hand if you run in any way, shape, or form. What do you run for track? Do you run track? What do you run?
100, 200, 400.
Okay, good. So you're tailor-made for this kind of problem. The 400-meter dash is often considered, if not the hardest, at least one of the hardest races in track and field. Yeah. It's because it's almost an all-out sprint. But if you go an all-out sprint, your legs tend to turn to like jelly around that 4th turn and stuff like that, right? So you really have to try to manage that. That's a pretty, would you say 53.2 seconds is a pretty good time for the 400? Yeah. Okay. So an athlete is able to run the 400-meter dash in 53.2 seconds. And we'd like to determine their average speed. Okay? So I would take, I'm looking for speed. It would be distance over time. So I would just write this out. I know people don't always write the equations out, but it shows us how we're doing that. we take 400 meters, I divide that by 53.2 seconds, and my calculator will give me that that is about that's about 7.52 meters per second. That's how I just do that calculation. Take a ratio of distance and time. This room is about 7.5 meters. So if I were to measure the length of this room, it's about 7.5 from that counter to that wall. What that would mean is that that runner, on average, is traveling about the length of this room every second. That's what that means. 7.5 meters per second. Every second, they travel the length of this room. Now, you run the 100, 200, and 400. Those are more sprint distance kinds of things. Some people will run like longer distance. Let's say that that person is now going to run the 1600. It's a mile. If they could maintain that pace for the mile, how long would that take? That would be another thing that we could do. So what I would do on this one, if the athlete were to run at that speed, completing a mile, how long would that take? I'm going to use time as distance over speed. The 1609 meters is covered at a speed of 7.52 meters per second. That would tell me how long it would take. Now, 1609 divided by 7.52, I'd use a calculator for that. I get 214 seconds. 214. All right, guys, 214 seconds. Doesn't mean a whole lot to me. I'd rather put that in so many minutes and so many seconds. Would you guys agree that it's at least 3 minutes, but less than 4 minutes? I'm dividing that by 60, and I see that it's at least 3 minutes. So I would say that that would be a 3 minute and then so many seconds. Now, some of you are strong with that. Some of you are going to be able to look at that and say, yeah, I can determine the number of seconds. Others are going to, I don't know how to do that. 60, 120, 180. That's the number of seconds in 3 minutes. I would take, from 214, I'd take away 180, and I get 34 remaining. So what that would be is a 3 minute, 34 second mile. Now, Noah, I know you are a sprint runner, a sprint distance, not a long distance. Is that a good time? Yeah, that's world record time. My point on that is that the 400 meter is almost an all-out sprint, and if you could maintain that for a mile, you'd be running world record pace for the mile. You can't do that, right? So you have to sort of slow yourself down. All right, a car maintains an average speed 35 miles per hour, MPH, for a road trip. How far was that road trip if they completed the journey in 2 hours, 25 minutes? So it's our last kind of problem here. The speed is 35 miles per hour. The time is 2 hours, 25 minutes. And I would like to know how far that road trip is. And I would like that in miles. So when I go through to do this, I'm going to use the other version of that equation, the third version. Distance is just speed times time. Now, I'm going to put this in parentheses there. In order for us to use these equations, we cannot have mixed units. I cannot have 2 hours, 25 minutes. I have to write that as a decimal number of hours. And the reason for that is I need the hour in this equation to reduce with the hour in that equation, so that those two things would cancel out. How I convert that 2 hours 25 minutes? I just take 2 plus 25/60. There's 25 minutes there's 60 minutes an hour, so I just take 2 plus 25 over 60, and that would give me the amount of time as a decimal. Then I just simply multiply that by 35. And that would give me about 84.6 miles. Okay? Folks, as math light as possible. We have some problems that we have to do, but we try to concentrate mostly on the concepts. But occasionally we're going to see some mathematics that we have to be able to do. Is there any questions on those things? Okay. I need your help then. We're going to do some activities with that red buggy car. So I need your help with this. We've done these kinds of things numerous times, but every time I do this, I need your help as a classroom to be able to do it. We need to clear off your tables. Give me your eyes here for a second. Eyes here. We need to clear off your tables, get them to the side counters. We need to have one person from your table grab a car and bring it back to your spot. We need another person from your table to go and grab a meter stick behind Riley. And we need yet another person to grab a stopwatch, which is going to be from me up front. So I need your help with this, folks. Clear the tables off, someone grab a car, someone grab a meter stick, someone see me for a stopwatch. Okay. Bryant, start, stop, reset. Start, stop, reset. Same thing, right? Start, stop, reset. Start, stop, reset. Start, stop, reset. Start, stop, start, stop. And last one. See your foot down. Okay. All right, guys. Everyone, stop for a second. I got to give you instructions. What? Whoa, hold on. I know you guys want to play. These are what are called constant speed cars. I turn this thing on. There's a battery, a couple of batteries inside. Let me get out here. I turn this thing on. A couple of batteries underneath here. Turn a motor. The motor that's inside is connected to a bunch of gears, and those turn these wheels at a constant rate. Now, I'm going to have you determine the speed of this car. The speed, again, is a distance over time value. Instead of me just giving you these numbers, you have to make measurements of some of these things for you to determine how to determine that speed. I want distance over time. You have a meter stick, you have a stopwatch, you have a car. What I'm going to ask you to do is allow that car to run the length of 1 meter. Time it. I'm going to ask you to then write down the speed. Let me get out of here. I'm going to ask you to write down the speed on a whiteboard. And I had you guys use the whiteboards before, with markers and things like that. So I still need some more equipment brought out to your tables. The person that did not get anything yet for your table, you got 3 things you get. The person that did not get anything yet from your table, go and grab yourself a whiteboard, please. Bring that over to your table. Go, go, go. I stole this from someone. That's you guys? Okay. So go grab that. And we need a marker to write with. I'm going to bring you a marker and an eraser. Okay? All right. Marker and an eraser. Marker and an eraser. All right, you guys, you are now free to go. I want to know the speed of that car. You guys are measuring distance, you're measuring time. You know, right? All right, have at it. See what you can do. I would like you to use the SI unit. What? No. As a 1 meter. Now wait a second. If I wasn't here. Okay, now look, if in my 4-year classes we spend a lot of time studying motion, we would study projectiles. We don't want to study projectiles. So someone keep that car from falling out there. I think I can. That card is so slow. That card seems to be pretty fast. Yeah. Right now, 5.32. It took about 2.84, 2.63. Oh, really? So if one of you else spends the fast. Alright, so I want to know the speed of that car. Yours is a slow car. No problem. So do you guys have a calculator or something to be able to calculate that? So you got 1 meter. And you divide that by 80.28. That number is that. Okay? There you go. Yep. You guys need a calculator at all? 297. Do you need a calculator to do this? Are you guys doing multiple trials? Yeah. Oh, that's a big difference. Okay. Let me know if you need a calculator. Oh my goodness. That thing is that is a
Oh yeah, I don't even take notes in this class.
Any better?
He's a great
Okay. So that's a little bit more repeatable.
I know, I was like, I feel like it's like common sense. Oh, because
Alright, so what do we have here? 337 meters per second?
we can
Alright. Do you guys need a calculator? Oh, you got it, 0.4? Alright guys, let me have you stop, please. Let me have you stop. I wanna make sure we know how to do that calculation. These guys that's your last run, right? I think you guys have the slowest of these vehicles, and I know that because the time to travel a meter was the longest. The time for you guys was about what was your last one? 4.13 seconds. And I think you guys might have had the fastest car. What was your time? 2.5. 2.5. So yours took 2.5 seconds. Yours took almost, not quite twice as much, but it's quite a bit slower. The batteries are a little bit weak on that one, right? Okay. How these people did it, may I show yours for a second? How they did this, actually, I'm going to use yours because you guys have it written so big so people can see it. All they're doing is they're taking the distance the car traveled and dividing it by the time it took. And from that, then the calculator would give you that number is, did you guys get that one yet? 1 divided by roughly 4.13. Sean, do you have my calculator still? Could you do that for them? 1 divided by 4.13. 1 divided by 4.13. 0.24. So you guys could have 0.24 meters per second. You guys have roughly 0.4. Sean, what did you guys get for yours? 0.37. What did you guys get? 0.33. And you guys need a calculator? Or? You got a 0.32. What did you guys get, Lola? Okay. Here's what I'm going to ask you to do. I would like you to make a prediction for how long it will take the car to travel this path. I want you to, now you're going to be a team for this. You're going to let the car travel along this side here, and then as soon as it gets to this spot, you have to have someone that's going to make the turn and allow it to go to there. So your job is to have it go across the table and just have it go along 2 legs. I want you to make a prediction of how long that will take. Don't run it until I see that prediction. Okay? So you're going to go along the length. I'm going to let you figure out how to do it. So this is like the 200-meter dash. The 200 is you're going around these things. So I want to know how long that should take. Yeah, so yours the battery so we can use that it might actually be
literally crazy.
It's literally about oh yeah. So 3 times yeah. Just right.
Okay, so before you run it, I want to see if you tell me that time. Before you run it, how long do you think it will take you to run it? I want to see that time before you run it. Wait a second, wait. I want to see your prediction where you're done. How did you do that? Would you guys agree that it's a time is distance over speed?
Yeah.
Time is distance over speed? So you have your distance, you have your speed, and then you might have to add something.
Save 180 times.
Yeah. Now run it and see how close you are. Okay? See how close you are. Alright, wait a second. What did you guys get?
Yeah, per person as a challenge. Taylor and I are on 20, Chris chose 19.
Are you just hold that from thin air for 20 seconds? 8.37. So, wait. This will be time is distance.
8.37. We'll try it one more time.
Distance is how
I'm assuming that was under.
This one's 15 meters per side.
We're going to get a little bit closer. This is roughly.
So that's what we get 7. We started
And then this, so 1.2, and then this. That's 1
just
and
try
about
to
1 is about 1. So the difference is about 350.
They did their science.
8.57.
Is distance over speed. You have to travel 3 meters.
Do it again. Just pop.
3 divided by 2. Okay, I know, your eyes are straight. That time is distance over speed tells you.
I would call that good. Oh, my fastest formation.
So 3 meters at that rate would give you a
Like I said, it's not going to go.
See how close you get? Wait, you guys got 9? Okay, run it. I like it. Go, run it. You got to be a team. Did you guys run it?
Yeah.
How close
We
you
got
got?
8.37 and 8.53.
Pretty good. That's pretty good. Okay, write it down. I want to see how close you got. Write it down. Did you guys make a prediction? About 11 seconds? Did you use this equation here? Did you say time is distance over speed? You could do that. Right? So look at the distance that it travels. You just add these two up. It's about 1.2 this way and about 1.8 that way. Add them up, you get 3. 3 divided by that number would tell you about how long that should take. Right? That's the speed is distance over time. Okay? So 3 divided by, what was that? 0.304? That number's about 9.8 inches per second. Run it. See if you get something close to that. Okay?
You should just sit here and let it sit upside down and run it.
Roll it above. And you roll it above. Oh my gosh. You got to let it roll. All right, we're almost done. You guys, we have to do that formula here. Did you guys run it? Okay, let me have you stop. We had some predictions here, and I'd just like to see how close you were able to get. The time is distance over speed is the equation we would use. So the distance traveled, would you guys agree it's about 3 meters? It's about 3, 1.2, 1.8-ish. It's about 3. I take that, divide that by your speed, and that would give you a time in seconds. And you guys were pretty close. What did you guys get for your prediction?
Our prediction was 8.5 seconds, and we got 8.37.
So they predicted about 8.5 seconds, and they measured about 8.3. That little bit of difference there is probably just uncertainty in our timing. Pretty accurate. All of us were probably in the neighborhood of 8 to 9 to maybe 10 seconds. You guys were about 7.6, except for you guys, because your car was so slow. It should take a lot longer to get through that. Were you guys able to get through the calculation? Yeah. You do 3 divided by, I think Sean said 0.24 or something like that. Yeah. So 3 divided by 0.24, that would be a 12 something?
Yeah, we did it.
Okay.
We had a faster car, but yeah.
That's okay. Guys, this is not meant to be a math heavy class, but we do have to do some things with speed equations from time to time. So hopefully a little bit of fun for you guys to see how that car works and how to use that mathematics. I need your help. Erase everything. Erase it. Return the cars to where you got them, the meter sticks where you got them, and the stopwatches. Help me with all those things, folks. You guys are doing fantastic. Yep, thank you. And then let's head on back. We have about 15 minutes to finish up our formative. I do.
Yeah.
All right. Yep, thank you. Markers and everything goes right here. Thank you. Sean, nice Sean. Sean, you look like you have a pretty decent math background. Is this right? Yep.
Yeah, it's James. Yeah. Mrs. Rollins. My favorite. So I brought.
Okay. So, folks, to finish the week strong, what I want to do for the remainder of time, we go to 9. This is enough time for us to do this, and for you guys to maybe even finish that assignment I'm going to do. The formative that I'm going to give you has to do with forces. Speed stuff. Those equations completely different topic at this point. Which of the following are in a state of equilibrium? This is to wrap your mind around forces again, so that when you take this formative, it's a little bit fresher. We have 3 different what are called force diagrams up there, A, B, and C. Which of those, if any, are in a state of equilibrium? Will you tell that person that you're sitting next to? Which, if any? Okay, I'm hearing A, and that's good. Equilibrium means the forces add to 0. Those forces would all add to 0. This one would have an unbalanced force up. This would have an unbalanced force to the right. Now, I sometimes will ask the question differently, even though it's the exact same thing. This question is stated differently, but it literally means the same thing. Which of the above will not change their motion? We know that forces are needed to change motion. Newton's first law says an object at rest stays at rest, an object in motion stays in motion unless forces are unbalanced. That is literally the same question. It'd be A. That one would not change how it's moving. B would be, if it's like skydiving, B would be sort of like slowing down. They pulled the parachute, and that would give them a higher drag force on their weight, and they'd be slowing down. C could be like someone pushing a car, and there's some resistance. That one would speed up going to the right. So those are literally the same question. But sometimes we state it about changing motion. Now, on your classroom page, you're going to see a formative. The formative will be, let's see, I'm going to post it for you right now. Okay, what I ask is that you just give me your best answers. When you're done with that formative, I'm going to have an assignment out to you on speed and velocity stuff. You are allowed, after you finish your formative, if you need your phone or a calculator, I'm going to say we're close to the end of class, you can go and grab, after you finish your formative, you can go and grab your phone. If you need to use that as a calculator, you can. At the end of the class, after you finish your formative. Okay? Do you have a question over here? I'll get you that. Okay, guys, go. You should have it. You need the classroom code?
Yes.
Yes. And folks, again, you can go and grab your phone if you need to. We still have about 7 or 8 minutes. You'll probably get your formative done, and you can get a good start, if not finish, that assignment. Okay? So, nice work with all those things. When you submitted the formative, did it give you the number correct that you got? No. No? So no feedback yet? I'll look at that and share some results with you guys.